you've probably never looked at mathematics like this before, but basically mathematics has a series of operations or operators, and they come in pairs. For example, addition, subtraction, multiplication, division, squares, square roots, cubes, cubic roots, powers, logs, etc. And I'm now going to start with the simplest of all questions that you know, and I'm going to do them slowly, slower than you'd ever do them. But hopefully, when we move on, we'll see the point of my doing that. So, addition. X plus 2 is 5. X plus 2 is 5. What's x? You probably should be able to guess that. You might say that x is 3. Is that okay? Now, but one way of doing that is saying you'd like x on this side of the page, and you don't like the plus 2, because it confuses the left-hand side of the page. So what's the paired operator opposite to plus? Minus. And we say plus 2, minus 2. What we do on one side, we do on the other side. X plus 2 minus 2, they cancel. X is 5 minus 2, and 5 minus 2 is 3. Now, you would have got that quicker, but that's the slow method of doing that. Okay? Now we look at subtraction. Y minus 2 is 8. Now, looking at it again, what's the twin of minus? What gets rid of a minus? Plus. So we say y minus 2 is 8. But we say plus 2 on this side and plus 2 on that side. And again, they cancel. Y is equal to 8 plus 2 is 10. Now, that was primary school, early years in primary school, and then you progressed. You liked maths then, and you did hard maths. You did multiplication. So multiplication then was 3x is 12. So 3 items to purchase in a shop, whatever they might be, 3 cards, 3 whatever, books or whatever, copybooks, pens, €12. How do you get the price of 1? Well, 3x is 12, you'd probably say x is 4. But what is that number? That's 3 times, isn't it? So it's 3 multiplied by x. And what's the pair of multiplication? Division. So let's divide this by 3 and divide this by 3. X is equal to 12 over 3. And 12 over 3 is 4. Is that okay? You moved on then to division, which was the next thing in primary. And you said, y over 5 is 10. Now, remember that really the way you like things, you like the letter to be on the left-hand side on its own and the answer to be on the right-hand side. It's a convention we have. But I don't like this 5 on the bottom. What gets rid of it? What gets rid of a divide? Multiply. So we say 5 on the top is 5 on the top. They cancel. They'll always cancel, because that's why you chose it. You chose the pair to get rid of it. So y is 5 times 10 is 50. And you're coming now towards the end of primary, and you're looking at sort of fancy numbers, and you're talking about squares. X squared is 9. Well, if you look at your calculator, well, sometimes you've got calculators with lots of buttons, but if you've just got a number of few buttons on it, sometimes you've got the inverse or the second function of the square beside it in the same place, just above it. So x squared, I don't like this 2 here. What gets rid of a square? What's the opposite of a square? It's a square root, isn't it? So if I take the square root of this and take the square root of that, well, what's the square root of a square? Well, we don't even have to know. We know it's the opposite. We know it gets rid of it, because that's why we chose it. X is the square root of 9, and the square root of 9 is 3. Or sometimes plus or minus 3, because minus 3 by minus 3 is 9 as well. So sometimes we need both answers. But you can see how we got rid of it. We just did the opposite. So here we see x squared is 9. The square root of the square is the square root. If we take the square root, we do it on both sides, and we get x is plus or minus 3. Now the opposite of that is if you were to start with the square root of x is 5. What would you do then? Well, the square root of x is 5. But I really don't like this square root bit on the left-hand side. I'd much prefer if that was x. So how do you get rid of a square root? What's its twin or its pair? How do you get rid of it? Square it, isn't it? So if I were to square that, I'd have to square that. And what's the square of the square root? Well, it doesn't really matter because it was chosen just to get rid of it. So x is equal to 5 squared is 25. Is that okay? So let's look now. We probably would have done this possibly in first year, maybe in sixth class with different teachers. But the cubic root, x cubed, is 8. Really not gone on the x cubed there. But what's going to get rid of a cubic root, or a cubed? What's its pair? On the calculator, what's the one that's opposite it, or the inverse of it? It's the third root, isn't it? So if I take the third root of this and the third root of that, well, that'll all get rid of it, and I'll get x is equal to the third root of 8. Now that might look complicated, but remember, these are just numbers. There's no x here. So this is just calculator space. Put in the 8, press the third root, and you get x is 2. Whereas you don't have any x here, it's easy to do that. They're just numbers. Is that okay? So what we're seeing here is that there's a whole series of pairs that come together in this. But are they the only ones that come together? Well, what would happen if the powers went a bit further and you're in sort of, well, into secondary now, and we're looking at x to the power of 10 is 1,024. You know your common term when they talk about a kilobyte or a kilo or something, megabytes and kilobytes and something. That's what they mean. They don't mean 1,000. They mean 1,024, or x to the power 2 to the power of 10. But how do we solve this thing here? X to the power of 10. What would get rid of it? I don't like this 10 here, do I? But if I were to take the 10th root of it, then I'd have to take the same on the other side, the 10th root of 1024. Now, that looks complicated enough, and so does that. But why did you choose them? Well, you chose them to get rid of it. So x is equal to the 10th root of 1024. And again, that's just calculator. 1024, x to the y, or whatever way your calculator says it, and you get x is 2. Imagine if they did it the other way around then, and they said the 5th root of x is 2. The 5th root of x is 2. Later on we'll see that that's the same as writing x to the power of a 5th is 2. But we'll worry about that at the moment. How do you get rid of the 5th root? The 5th root is something that says, if you do this 5 times by each other, that by that, by that, by that, by that, 5 times, you'll get 2. Well, why don't you maybe just take the 5th power of it here, and do the 5th power here? Because the 5th power will get rid of the 5th root. X is equal to 2 to the power of 5. And that on a calculator, x is 32. Is that okay? Now, it's only a few minutes ago since we were doing x plus 2 is 3. And that was addition. And we said, we know that. It's exactly the same method. Exactly the same as we were only 5-10 minutes ago. Let's go further. What two things come together later on then? Sine and inverse sine. These two people or pairs go around together. Cosine and inverse cosine, tan and inverse cosine, or tan and inverse tan. They're twinned, they're pairs. So, and similarly here. So just imagine that somebody said here that sine of x is 0.5. Sine of x is 0.5. What are we always doing with equations? We always wanted the x on the left-hand side, with nothing else around. We wanted it on its own, and the rest was just pure numbers or stuff on the right-hand side. What's the twin of sine? What's its partner? Inverse sine. Okay? So if you were to say sine x here is equal to 0.5, you could take the inverse sine of this side and get the inverse sine of this side. Now it looks ugly, but remember why you did it. The inverse sine and the sine were done so they'd cancel. You get x is equal to inverse sine 0.5. Now that might still look a bit tricky, but remember that 0.5 is a number. An inverse sine is just something on your calculator. There's no x's there. Now you've solved for x. Is that okay? So if I wanted to get sine of 0.5, if somebody said sine x is 0.5, I can take the inverse sine and the inverse sine. I'll do this more carefully. So sine x inverse sine is inverse sine. X is equal to inverse sine 0.5. And if I do that on a calculator with the degrees on, not the radians, I'll get x is 30 degrees. If there was another question like it, and they didn't start with the sine, but they started with an inverse function, here we've got inverse tan. Inverse tan inverse x is 45. What's x? I've no idea. What gets rid of an inverse tan? What do you have to put on this side to get rid of it, to wipe it out? Just tan. So tan of this side must be tan of this side. Tan inverse tan gives you just x. X is tan 45. And that's not too difficult. That's just sticking 45 in your calculator and hitting the tan button. You get x is equal to 1. So I'll finish with these sections, but it works for both sine, cosine, and tan. And I move on to logs. Now, they don't give you logs on the ordinary, but for some reason, they give you the pair. They give you the twin, which is the power, but they don't fully give you the actual log of it. So for example here, if somebody said 10 to the power of x is 1,000, what's x here? Unfortunately, really the only way for you to do that is to try different values of x in a way. 10 to the 1 would be 10, 10 to the 2 would be 100, 10 to the 3 would be 1,000. Oh, it's 3. But a more reliable way is if you have 10 to the power of something, you can get rid of it by using the button beside it on the calculator called log. So what you say is log of 10 to the power of x is log of 1,000. I don't like log, and I don't like 10 to the power of x, but because they're pairs, I chose them because they got rid of it. And it just became x is equal to log of 1,000. And that's just 1,000 on the calculator. Hit log, x is 3. So if you get a question like that, 10 to the power of something, you just take the log of it. The other version that comes with it sometimes is ln, log, and that's when you have e to the x. But again, I'm just showing you that there are pairs. Most unlikely to get that, but certainly in terms of 10 to the x, it's far more reliable to take the log, because you get the answer, you're not guessing. Finally, the last topic you do pretty much on the Leaving Cert course is differentiation. And differentiation takes this expression here, you probably all would know how to do it, 7x squared plus 2x plus 3. And if I said, what's dy dx of x squared, you'd say it's 2x. You take down the number and you reduce it by 1. So you'd get 14x plus 2. Now, so let's imagine that we have y is equal to x squared, and y is equal to x cubed, and y is equal to x to the 4. dy dx of x squared is you take down the 2, leave the x, and reduce this number by 1, it becomes 1, or just 2x. dy dx here, you take down the number, 3, leave the x, and reduce the number by 1, 2. dy dx here is take down the number 4, leave the x, and reduce it. But in addition to differentiation, there's actually a process called integration with this nice fancy symbol behind it. And what is it? Well, in this case, you took down the number and reduced it by 1. What's the opposite of that? Well, the opposite would be increase the number. And you used to multiply and divide. So, for example, if I took the integration of, this might sound scary, x to the 1, the integral will be increase the number, x to the 2, but divide. The integral of x squared would be increase x cubed, but divide. What's dy dx of x cubed? Going backwards, 3x squared. A third of it would be x squared. So all I'm saying is that in every part of mathematics there's a way forward and a way back. And they're all the pairs, and there's nothing more mysterious than that. Okay? But hopefully for the remainder of the session, the remainder of the day, and more particularly for your leaving certificate and beyond, you'll just see an awful lot of these things as irritations in the way. X plus 2 is 5. I don't like the 2. It's a plus. Make it a minus. Get rid of it. Sine x is this. I don't like the sine. What gets rid of it? Oh, yeah, an inverse sine, and get rid of it. And you can hammer any single equation in algebra with these sledgehammers. You've had them, most of them from primary school, some of them in early secondary, and you just have to get used to using the sine and the cosine and the inverse way, this way, rather than seeing it as a bit of a mystery. Is that okay? Okay. I'm now going to turn to a topic that I call manipulating equations. I'm going to start that in about 30 seconds, okay? Just going to get a glass of water. You can hear me again, yes? I'm on the speaker? Cool. Manipulating equations. You will get this in your examination in several places. So I've just chosen the following expression. A over B is C over D. And what I'm going to be working on is getting the answer for A, or for B, or for C, or for D in terms of the other. In other words, at different occasions I'd like a particular letter to be on the left-hand side so I can solve the rest. So starting here with A over B is C over D, express A in terms of B and C. So have a look at that there. A over B is C over D, and I would just like to have A on the left-hand side. So to have A on the left-hand side, there's really only one thing annoying me. It's the divide by B, isn't it? So what I'm going to do is I'm going to get rid of the divide by B by multiplying by B. That will get rid of that purposely because that's why I did it, and A is equal to BC over D. And that's how we do that question there. So I just look at the bit I don't like, I find the opposite of the operator. In this case, multiplication becomes, or division becomes multiplication, etc. Okay, same question, A over B is C over D, but now I'm interested in the term D. I'd like this one. I'd like D to be on the left-hand side, on its own with nothing else there. Okay? So, A over B is C over D. Well, the first thing I don't like, possibly, is that D is on the bottom, where really it would be better if it was on the top. Is that okay? So, and it's dividing by D, so if I multiplied here by D, I'd have to multiply here by D. And that would get rid of that. So where would it be at that stage? Then we'd have AD over B is C. It's not great, but it's better because D is on the left-hand side. Now I can slowly get rid of these things. The B I don't like, so I'm going to multiply by B. So I get AD is BC. Not gone on the A now. I think I'm going to divide by A. Looks like I've got D is equal to BC over A. Is that okay? Now I did that reasonably slowly. A number of you would have taken a much quicker step that you've learned a long time ago. A over B is C over D, and you would have cross-multiplied in some way. And you would have said A times D is C times B. And if you were looking for D, you'd have divided by A, and you'd have got D is equal to CB over A. D is equal to CB or BC over A, the same answer. This is your cross-multiplication method. You're familiar with it. But this is the slow but consistent, step-by-step, will get you there, always, process. So that was the cross-multiplication approach in your notes. Now we'll move on a little bit, and we'll say A over B plus C over D is E. So you have more on the left, and now I'm looking for express A in terms of that. So A over B plus C over D is E, and my field of interest is A. Well, all I'm doing is getting rid of anything I don't like on the left-hand side. I'm not gone on this plus C over D stuff. It's a plus. So I say A over B plus C over D is E. But I know that if I were to say minus C over D on both sides, that would get rid of that stuff. And I'd be left with A over B is E minus C over D. Now, I just have to get rid of the B, and I could do that this way. A is equal to B into E minus C over D. So there's pretty well nothing I can't do. I'll just do the last one of that, and I'll express D in terms of A, B, C, and E. Here I've got pretty well the same formula. A over B, C over D, but I'm interested in now, my focus is on D. So, probably have enough familiarity with this now, but let's do it. A over B plus C over D is E. My focus is D. I don't like D on the bottom. I don't like it there anyway, but maybe I'll just get rid of this plus or minus bit first. C over D, A over B minus A over B plus C over D is E minus A over B. I'm getting rid of the A over B. So C over D is E minus A over B. D is still on the bottom, so I'm going to put it up here and here. So I now have C is equal to D into E minus A over B. That's not particularly pretty. That's D on the right-hand side. It's got a multiplication beside it. But let's see if I divide it by the mess, E minus A over B, E minus A over B. I chose the mess because it was the same mess above, so it will cancel. So now I'm left with C over E minus A over B is D, and I could write that as D equals C over this. By just flipping it around, I can say, go again, D is equal to C over E minus A over B. Okay? So, for your leaving certificate, there is no equation, whatever, that you cannot resolve. Step by step, you can get rid of an addition, a subtraction, multiplication, division, a log, a power, a square root, a cube root, a trigonometric function, an inverse trigonometric function, a dy dx. So there's nothing you can't solve algebraically. And algebra is about solving step by step these things. I just thought I'd show you one thing that is worthwhile. You've got a whole series of notes in your log tables, a whole series of equations. And let's just look at one formula that you're given for the area or the volume of a sphere. It says that V is equal to pi, 4 over 3, I think, pi r cubed. Now, sometimes in the leaving certificate, you may get marks for working with spheres where they might tell you what the radius is. But it's pretty rare, really. They're far more likely to tell you what V is, and you to find out what R is. In other words, for every equation, there's a few others tossed around. So really what's happening here is their focus of interest is R, not V. V is given. The volume of a sphere is known to be 10 cubic meters. Find its radius. Oh, don't have an equation for that. Well, let's look at it. We're interested in R, aren't we? And if we want that to be on the right-hand side, we could say that's equal to V. So we could start the equation by saying 4 over 3 pi r cubed is V. At least R is on the right-hand side for us here. Is that 3 dividing? Yeah. So let's multiply by 3 then. Is the 4 multiplying? Well, it's 4 pi r cubed now is 3V. Is the 4 multiplying? Is that a multiplier? Is pi a number just like a number 3? So 4 pi is actually a number. That's just a multiplier. I could divide by 4 pi here. So at this stage, I'm down to really just r cubed is equal to 3v over 4 pi. But I don't like r cubed. What gets rid of a cube? What's the sledgehammer that gets rid of a cube for us? On the calculator? It's the cubic root, isn't it? So the cubic root of r cubed is equal to the cubic root of 3v over 4 pi. And what's the cubic root of a cube anyway? It's just another way of saying r. r is equal to the cubic root of 3v over 4 pi. Now remember, they've told you what v is. V was 100 or 1,000 or a number. That's a number. 3 is a number. 4 is a number. Pi is a number. The cubic root is on your calculator. You found r. Is that okay? So for the whole area of shapes and sizes, perimeters, volumes, all of these things, you just rip the thing inside out and say, I can take this step by step. And there's no right way. There's multiple right ways. So if I had done the crisscross method, or I had chosen to get rid of the minus before the plus, or this before, it all comes out in the wash. All you want is the one letter you're interested in on the left-hand side, and the rest on the right. And that's it. So what sort of questions are there? Well, there's loads of those type of questions. They're hidden in things you've got to do to get from the start of something towards the middle and out the other end. They won't say, rewrite the equation for volume, but they'll say, the volume is known, find the radius. So they're there. So I want to start now with some different part of the course, and this is just plugging in numbers. These questions come up all the time. Evaluate this thing here when P is 1 and Q is 2. So all they're saying is plug the numbers of P equals 1 and Q equal to 2 into this. So you might just take a minute to do that with your calculators, okay? I'm back, I think. Okay. These questions here require just the one rule. I'm going to start now in a moment. I'll start in about 30 seconds. These questions here require the one rule of BIMDAS. I think you may have heard that term, or BOMDAS, or whatever you call it. Brackets, what do they call it? Brackets and what? We'll start that again. Of, or something like that. Indices, is it? Okay. Start in 30. Okay, we're going to evaluate some expressions, and we're starting here with p squared plus 4q over this thing on the bottom. We're just asked to plug in numbers, really. This is arithmetic, but the order in which you do things is important. For example, 3 plus 4 times 3 plus 2 minus 1 is not the same as 3 plus 4 times 3 plus 2 minus 1. You can't just assume there are brackets wherever you want them to be. And there is an order for this. And they say, where there is multiplication in an expression, you do that first. So there's naturally brackets around that. So that would be 3 plus 12 plus 2 minus 1. And because they're just additions and subtractions, then the order now can be done in sequence. 3 plus 12 is 15, plus 2, 17, minus 1 is 16. But you can't just assume that that's 3 plus 4 is 7. The way I had written it, you might think that it's 3 plus 4 is 7, times 3 is 21, plus 2, 23, minus 1 is 22. It's not. You do multiplication first. And this convention came about, and they call it BIMDAS, B-I-M-D-I-S, where you do your brackets first, and then if you want to talk about multiplication, division, addition, and subtraction, and here we're talking about the powers, you know, or but in America what they call that is, in Ireland we call that BIMDAS, or BOMDAS, brackets of, we are talking about the power of something. In America they call it PEMDAS. Parentheses, exponents, again, multiplication, division, addition, and subtraction. Anybody going to high school in America would have to suffer, please excuse my dear Aunt Sally. It's very sad. But that's what they have to remember it by, okay, for BOMDAS. So let's look at some of these things here and go back to the question we're faced with, or we're given. P squared plus 4q over 2 into q plus 1. P is 1, q is 2. So we start now with p squared is 1 squared. 4q is 4 times 2. 2 times into q plus 1, 2 plus 1. And the brackets are very important. So now we can do the brackets. Because this is an indices, the I, or a power, we must do that first. So 1 squared is first, and 4, 2. 1 squared is 1. 4 times 2 gives us 8. 2 plus 1 on the bottom first is 3, and 2 times 3 is 6. 1 plus 8 over 6, 1.5. Another question, evaluate this expression here, where A is 1, B is 3, and C is 5. Nothing new, really, to add here, other than the same BIMDAS or BOMDAS. We do it in that order. We plug in the numbers. A is 1, so that's 1 squared. The B, we do 3. The C, we do 5. On the bottom, 2. B is 3, and C is 5. And we take those step by step by step. 1 squared is 1, 3 is 3, 5 is 5. 3 minus 5 is minus 2. 2 times that minus 4, and we get our answer. So that's it done, really, and we're going to move now to a new topic where we're drawing or solving quadratic equations or functions. We'll see this on the program in a number of places, particularly graphics, in the graphics section, where everything is visually clear. And it's really a nice way to come at the understanding of a picture where you can see it. But let's go through it first from the algebra point of view. Let's say we don't have time in the examination. They're not asking us to draw it, so we've got to go with the pure algebra first. So for the function fx equals x squared minus 2x minus 8, find the value of the integer values of x from minus 5 to plus 5. When we're drawing graphs, by the way, we've only got paper, so we've only got 2 dimensions. The 2 dimensions we use are vertical and horizontal, y usually and x. It doesn't have to be y and x. It could be age and height, or height and weight, or age and salary, or anything. But it'll only ever be 2 things, because we've only got paper. If we had three things, well, we could build computer models or we could build physical models in 3D space. But in the exam, we're stuck to two. So this fx is really another expression for y. Nothing more, y is equal to this here. Just the function is this. And we're now going to ask, what is the value of this function when x starts at -5 or when x goes up to +5? So what is the value of fx x squared minus 2x minus 8 when x is equal to, say, 2? What is f of 2? And just as we did before, anywhere there was an x, we plug in the number 2. So 2 squared minus 2 times 2 minus 8. F of 3, we would say plug in the number 3 everywhere you see an x. 3 squared minus 2 times 3 minus 8. F of 4, etc. So we get a whole table of them, starting at -5. -5, we say -5 squared, because everywhere we see an x, we put in the minus. Minus 2x, remember to keep the -5 in the brackets, because, and then -8. We work out all those numbers. And equally for the values above 0 up to 5. So now we have a few questions. Given the values of the variables, verify that a point satisfies a function. These are the specific questions you're asked. What we've done is we've taken every syllabus statement in your official syllabus guide for Project Maths. If you look at the syllabus for 2013, every single strand has a series of topics under it. And every topic has a series of sentences or prescribed learning requirements. What we've done in these notes is we've taken every single one of those and developed a question for it. So this here, you are expected to know to prove if a point xy, 616, actually fits on a graph or not, or satisfies a function. So that's one of the hundreds, I suppose, of small steps and small tasks you have to do across the course. But every single one of them is covered. So show that the function here, f of x, what is f of 6? So plug in f of 6 there and see what you get for x squared minus 2x minus 8. Give that a try. Plug in the value 6. Everywhere you see x, plug in the value. Okay, so we plug that in. When x is 6, x squared is 6 squared. Minus 2 times 6 minus 8. 6 times 6 is 36. Minus this is 12 minus 8. That 36 minus 12 is 24. Minus 8 is 16. Every point on every graph is identified by xy. The x you were told was 6, and the y here was the value you got, 616. It looks like 616 is indeed on the function. It does satisfy the equation. It needn't have had, but in this particular case it did. Now, check whether or not the point xy24 satisfies the function. So, a different graph here. We say y, in this case, is g of x, because everything is really y. If you've got x on one side, you have y on the other. You've only two variables. So we're saying let's see if the point 2, 4, the point is always x, y, satisfies the function. Well, let's put in x of 2 in here. So we'd say y is equal to minus 2 minus 8. So y would be minus 10. So this would suggest that the point would be when x is 2, y is minus 10, not 2, 4. That point is not on the graph. Now, when you're dealing with functions for most of your course, your functions are well behaved. They never have more than one value for x or y at a given point. With one exception, the one exception on your course is in the case of something like a circle, and I'll draw better circles than that. But in this particular case here, that x value has two y values, one above and one below the line. But the vast majority of your functions are quadratic, or cubic, or linear, and they only have one value. So if the point 210 is on the graph, 28, 26, 2, all the other ones can't be. If this point here, 5, 3 is on the graph, 5, 7 or 5 minus 3 can't be, because it's not going to swing around. So with the point, find the point 2, 4 is not on that. Okay. Here's where they throw in a small bit of algebra, and they throw in a bit of additional algebra, and they say let f of x is equal to x squared plus ax plus t. Find the value of t given that f of minus 5 is f of minus 1. Now this is a bit trickier now. What they're saying is that the value of the function f of minus 5 is the same as f of minus 1. So plug in the answers here for f of minus 5 into minus 5 squared plus a to the minus 5 plus t, and f of minus 1 equals minus 1 squared plus a to the minus 1 plus t. So I'll leave that to you for a moment. Two equations. They're saying that f of minus 5 squared plus a to the minus 5 plus t, that's f of 5, and f of minus 1 squared plus a to the minus 1 plus t. And what did they say about the two values? That they were equal. So that this thing here is equal to this. So let's work out what the first row would be. What's minus 5 by minus 5? 5 by 5? 25. Minus by minus plus. So 25 minus 5a plus t is equal to 1 minus a plus t. Do you want to go and solve that now? Do you want to try that? So give that a try, see if you can solve that. Okay, are we there again? When you see equations like this, you're probably used to taking something over to the left-hand side or over to the right-hand side to solve it. But just going back to what we did earlier, let's say we don't like this plus t here. Well, we could say minus t here and minus t here. As it turns out, that cancels, and so does that. But if we take a number across, 25 minus 5a equals 1 minus a, we say, I don't really like this minus a bit here. How would I get rid of it? Well, I'd call it a plus a here, I think, and therefore a plus a here. And look what's happened. The a has come over here as a plus. That's all that's gone on. So 25 minus 5a plus a minus 4a is 1. Not really gone on the 1. That's a plus 1, isn't it? So minus 1 here would give me minus 1 here. So 24, or 25 minus 1, minus 4a is 0. Don't like the 4a. I could maybe make it 24 minus 4a plus 4a is 4a. So 24 is 4a. Don't like the 4. A is 6. So you can always solve equations, and you'll be doing a lot of rearranging of equations in the particular exam. There's an equation here on the quadratic equation with the use of the minus b, and this also comes up in the graphics equation. So we'll just do it here first. We have an equation here, an expression that says y is equal to ax squared plus bx plus c is 0. And this is in your formulae tables, and it says the actual answer is that the roots of this is equal to 0 when x is equal to minus b plus or minus b squared minus 4ac over 2a. The important thing to do is to remember the signs involved. So, for example, in the next page, if we look at this particular expression here, x squared plus 6x plus t equals 0. If we have to map that to ax squared plus bx plus c, what I do is I just draw a box here to the side, and I say the x squareds are the same. A must be a number. This must be 1. A is 1. B must be a number. B is 6. And it's positive 6. And C is t. And then I use those equations and those numbers in the equations that follow, and I solve the expressions that go forward. Now, an alternative approach sometimes is if you can solve equations, you can do them by factors. And we'll be doing those shortly. So, in the exam, you're given an expression where c is equal to 8a minus 5b over 2d. Find b in terms of a, c, and d. What they're saying is find b. B is here. So they're saying change your focus of interest just to here. And we've done plenty of those already. We just change the focus to the letter, get rid of all the things around it, and go around. Similarly here, the volume of a sphere is given by this, and we've shown earlier that we can just focus our attention on or, work through the steps involved, and find that or turns out to be the cubic root of 3v over 4 pi. Another thing that comes up in algebra, this A lot of the same work again and again and again. But once you build up the skills, you have them then forever, and you're relying on them comfortably, and you can get on with more interesting questions. But they do give you some that are a little bit tedious. They're just plugging in numbers. But expand and simplify the following expression. They give you this long thing here. 2p squared plus 3 minus 3p times this plus p into that. Expand that expression. So the way we do that is that we take each of the terms in turn and we say, if we're multiplying into, that's a bracket, we multiply everything in the bracket by the 2. So the 2p squared and the 2 times 3 is 6. Here again, we're multiplying into the bracket 3p into p minus 2. 3p times p would be 3p squared. 3p by 2 would be minus 6p. But, to be very careful, there was a minus sign beforehand. So because this was a minus, then this becomes minus and that becomes plus. And again, multiplying the last bit, p into p minus 6. P times p is p squared minus 6p. And we just write all of the things out together. Then we group the terms that are common. And we take the p squared with the p squared and the p squareds together. Then the p's together and then the numbers together. Just as if you were sorting out things in a bag. If there were bananas, apples and oranges there, and everybody had gone out on Halloween and got some stuff, and got some chocolate bars and sweets and nuts and all that stuff, you could put all the bars on one side, all the nuts on one side, all the bananas and the oranges together. All you're doing is collecting like things together, that's all, and joining them up. This is just a bit messier when there's more. But what they talk about when they do this in high school, when they multiply a plus b by c plus d, you multiply everything in this by everything in that. And they call it the FOIL method. The first thing they do is the first one in each, a times c. Then the outsides, a times d. Then the insides, b times c. And then the last, b times d. And that's how they get the four things together there. We would probably do it this way here. We would say, use the first term first, the a, and multiply it by both. So you get AC for this bit, and then AD. And then the second bit, BC plus BD. Exactly the same, we just don't talk through it the same steps. If there are three things, you multiply the first by the first, second and third, second by the first, second and third, and it just goes on forever. Nothing more interesting really than that. It's just tedious, and you go through it. This part is about inequalities. Inequalities are where instead of having x equal to something, we say that x is greater than or less than or equal to something. Or maybe x is less than or equal to something. John has more money than I have. Mary is faster than. Mary's at least as fast as. All those words, at least as, faster, better, stronger, fitter, whatever. They're all greater thans or less thans, or at least as. And we write those with this symbol here. So here we have an expression where they say simplify some of these with greater thans or equal tos. 3 times this where x is greater than or equal to 12. Well, how do we deal with that? Well, generally we leave things pretty well alone. 3x plus 3 minus x greater than or equal to 12. We treat it pretty much as if it was an equation. Brackets here, 3 times x, 3 times 3 is 9, minus x greater than or equal to 12. 3x minus x, they're the same. That becomes 2x plus 9 greater than or equal to 12. We can take things away on either side, just as it was an equation. I don't like the 9 on this side, so I'm going to say 2x plus 9 minus 9 is 12 minus 9. So I get 2x is greater than or equal to 3. I don't like the 2. I'm going to divide by 2. X is greater than or equal to 1.5. And we didn't really have to touch anything too much with the sign. I'll show later how we can touch the sign. So let's simplify the following thing here now. X plus 1 less than or equal to 2. X over x plus 1 less than 2. This isn't a less than or equal to. We're saying specifically I have less money or less time or whatever. Whatever it'll be. Less energy than somebody else. Again, we can divide and multiply above and below without changing anything at all. So x over x plus 1 less than 2. Not really gone on this x plus 1 here. So I think I'll multiply by x plus 1. X less than 2x plus 2. Not really gone on the 2x and the x here. I think I'd like to get rid of one of the x's here. So maybe x minus x is 2x minus x plus 2. So naught less than x plus 2. Getting close. Don't like the 2 on this side though. So I'm going to take it away. So I'm going to say naught less than x plus 2 minus 2. There must be a minus 2 here. Minus 2 less than x. Now, generally you wouldn't leave the equation like that. You wouldn't say minus 2 less than x. You'd actually say x greater than minus 2. But notice the sign has changed. What's happened here is that I'm reading left to right, right to left. If I read this way and move from x to the minus 2, the wide part is the first thing I see. So x greater than minus 2 is the way I read it. X greater than minus 2. Other ways I could do it. I could say minus 2 less than x. Don't really like that. I could take x on this side. I'd be left at minus 2 minus x less than naught. I could add 2 on this side then. Minus 2 plus 2 minus x is greater than 2. Minus x less than 2. But I'd still be left with this minus now. So the only thing you've got to watch is if you have an inequality and you decide to multiply by a minus, then you're saying x is greater than minus 2. Not only do you change both signs, but you actually change the sign, the greater than sign in the middle as well. The other way of looking at it is if you have it in this shape here, just read it x wide going pointy to minus 2, x wide going pointy minus 2, x greater than minus 2, minus 2 less than x. On the number line, that would be done as follows. If we just imagine, say, a straight edge or something like that. And imagine that's the number line and say that's 0, minus 1, minus 2. And the point now is, we're told that we had it in a few places, x is greater than minus 2. So it looks like is x here is anywhere greater than this. In fact, the way they draw that is they would not include the 2 in there at all. They would draw it like this, minus 1, because the 2 isn't included. Greater than minus 2. If it was greater than or equal to, you'd actually fill that in as well. So with the last few moments of this session, I'm going to just go through a small bit of things on sets, if that's okay. Just the use of the numbers are the number sets, the sets of numbers n, z, q, r, and c. And I'll do this by drawing on some of the work you did before in the junior certificate with intersection of sets. But really what I'm doing is I'm going to introduce you again to the number sets. You'll see these sometimes, not as often in project maths, but they'll explain it in longer words now. They won't say things as often as x is an element of R, but they'll say where the number of possibilities are all real numbers, or they're integer values, or they're negative values, or they're, rational numbers. But really all they're saying is n, z, q, r, and c, and how those numbers came about. So let's just take a tiny walk through that, if you don't mind. I'm just going to go through that, and I will do this again in a different section. But let's just take 5 minutes to explain how these things came about. This is the number 0, 1, 2, 3, 4. Imagine it's sort of a primitive society, and they're trying to figure out things like numbers. And they start counting things. They might count stones, or they might count animals, or animal pelts, or whatever. Fish they might have caught, or anything they have. And all they know is numbers that are real, numbers that are real to them, but they're natural numbers. Numbers like 1, 2, 3, and 4. And for a long time, you can imagine that n, 0 doesn't mean anything. You either have a fish or you don't. What's this 0 stuff? So they start doing this, and then they start doing addition. And they say, if I had one fish and then I had a second one, I'd have 2, 1 plus 1. And everything is okay. 1 and 2 would give me 3, and that would be really nice. And you get the basics of some sort of idea or some sort of sets here. 2 plus 3 is 5. And they're really impressed with this whole notion of addition. And they've got this number set and it works fine. And then somebody introduces the pair called subtraction. And they say, what would happen if I had to give some of the fish back? And they said, oh, that's okay. If you had 4 fish and you had to give 1 back, you'd be at 3. Or if you had to give 2 back, you'd be at 2. And then somebody says, what happens if you have to give the 4 of them back? And they say, oh, where would that be? So they had to make up the number 0. 0 was not having any fish. Which didn't make a lot of sense. You either had fish, you didn't. Now you have a number for it called 0. What would happen if you had to give 5 back and you only had 4? Well, then you'd owe somebody a fish. Oh, what's that about? And the whole concept of negative numbers, not only not having a fish, but even if you did, you'd have to give it to somebody. And they said, let's dream up this sort of stuff. So then they dreamt up this thing called Z. And Z was okay because it did addition and it did subtraction. You could add stuff and take away stuff forever. It's almost like east and west. You could go so many paces east, and then so many paces west, and more paces west, and end up much further back, and you'd still be in Z. Everything would be fine. Until some brain box decided to think about multiplication. Multiplication was a pretty interesting, cool thing, because really multiplication was just a way of getting rid of boredom. If somebody said you did 2 steps, and then 2 steps again, and then 2 steps again, let's just multiply it. So 3 times 2 would be 6. 2 times 4 would be 8. 5 times 4 would be 20. So they had this really cool thing of 3 times 2 would be one of those 3, and again, so 3 times 2 would be 6. Or in fact, more correctly, 2 times 3 would be 6, because 3 times 2 would be written like this. There's a 2, there's another one, there's another one. And this was really good. Until some idiot decided that they needed division. How would you get back? Well, if you divided 6 by 3, it'd be 2. Divided 6 by 2, it'd be 3. What happens if you divided 6 by 17? Oh. That's a mess. So, for the first time now, we see that the numbers are no longer just points that you land on, but you can land in the middle. Like 1 divided by 2 is sort of here. It's at a half. 3 divided by 2 is 1 1/2. 5 divided by 4 is 1 1/4. There's a whole load of stuff here. This is a mess. So they said, we need another letter, and they called that Q. Quotients. Everything divided by everything else is a quotient. Now we're sorted. We've got multiplication and we got division sorted. Everything is cool. And it was pretty okay. Until somebody decided on squares. And they said 3 squared is 9. The square root of 9 is 3. And they even had things like 5 over 4 squared is, and the square root of 5 over 4 was all fine. They were all rational in a ratio numbers. Until somebody tried to figure out what the square root of 2 is. Now I won't do this here. Well, I will in a minute. But somebody decided that the square root of 2 has to be, in the lowest possible form, 2 numbers, one over the other, like A over B. It has to be like 5 over 3 or something, or 7 over 13 or something. There has to be 2 numbers that's equal to that. Has to be. Is that okay? And they're the smallest 2 numbers it can be. And the genius then decided, well, if that's the case, if you were to square that, you'd get 2 is equal to A squared over B squared. And you'd get 2B squared would be A squared. And then they figured out that if A squared was equal to 2B squared, this number here had to be an even number. Because 2 times that number had to be even. Is that okay? That made sense. Isn't that right? And if this is an even number, what's the square root of an even number? Has to be even, doesn't it? Because odd by odd gives you odd, and even by... So this had to be an even number. So A had to be even. Now, if A was even, which is great, A is really the same as 2 times an odd number, or maybe 2 times an even number, but A is even, it's like 2C. And they did the same logic then, bit of a twist, and they said if A is 2C, well then that the square root of 2 is 2C over B. 2 would be 4C squared over B squared. 2B squared is 4C squared. B squared is 2C squared. This is an even number. B must be even. B must be even. Well, if A and B are even, that can't be the simplest way of writing it. And this puzzled them. And it basically figures out that the square root of 2 can't be put in a ratio. These are irrational numbers. These things are just weird again. So they said, we better call these things something else. We better call these things OR. So now we've got the number line, not only with the ratios, but somewhere in the middle, these sort of funny numbers like pi. like the square root of 2, square root of 3, that just can't be put in a ratio. And then they said, this is a bit of a mess. And that was okay until the last part of the story. The last part of the story was they decided to do square roots. And the square root was okay when they were doing the square root of 36. And they got 6. Or the square root of 0.6, and they got a number. But what happened when they got the square root of -3? They said, this is a mess. This is just dreadful stuff. And they said, we better dream up something for this. What's the square root of -1? They said, let's call it I. Let's call it complex numbers. So they made up another set of numbers called C. And nobody thought they were of any use particularly for a long time when they did complex numbers. They sort of said, it's nice to have them. They're sort of fairly... Sure, why would you want a complex number? It's imaginary or something? Why would you want that? Lunatic stuff. But basically what it did was it transformed the number line. The number line used to be a line. One direction. 1, 2, 3, -1. Always in the line. You could never go north or south, only east and west. But now you have a number that could be here. 2 plus I. -1 minus 2I. Numbers could be on a plane, an Argand diagram. And if you were working out the distance of this point in the past, you'd have said, what's the positive value of 3? Now you say, what's the positive value of 2 plus I, or the absolute value, or the 2 squared plus 1 squared, or the Pythagoras, the modulus of these numbers. But by far the most important thing about these numbers, more than anything else, is if you multiply complex numbers by each other, they rotate. They don't just get bigger, they rotate. So if you multiply the number 4 by I, it becomes 4I. Multiply it again, 4I squared minus 4. So every time you multiply by I, it rotates. Every time you divide, it rotates the other way. It would not be possible to play any computer game anywhere without complex numbers. Complex number multiplication takes a two-dimensional icon, Super Mario or whatever, and just turns that person upside down, inside out, and rotates through complex numbers. Every games company in Ireland is using this solidly all the time, to rotate and to maximize and to grow and expand on the screen that you have in front of you. And that's the complex number C. That's the end of the story. Have a good break. Thanks for your attention. Okay?